Hello, welcome once again. We continue our session 5. This time we're going to talk about dependability systems. Now I need to emphasize on the point here that dependability of a system is one of the most important things to every user. Let me give you a typical example. Significant number of you, not significant, I will put it like a significant number of, a handful of you have one way or the other, or one occasion or the other, pointed fingers at Sakai, having failed you at some point in time. I think I met somebody who was trying to explain the constraints you guys are facing in completing a quiz of some sort for your data structures class. I wouldn't want to mention names here, simply because I may be using this video in the future for other lectures. So your data structures class, so the constraint is the time you guys want to take the quiz. Sakai receives a lot of traffic and some people get dropouts and the platform begins to misbehave. At that point, there are complaints here and there. In fact, some of you have perpetual distaste for Sakai. You even forget the fact that you came to do IT, and for that matter, it makes a whole lot of sense to do everything in a technological approach. And so you forget yourself about these things, and you would wish that, I mean, can you imagine some of the assignments I asked you to complete? Use the right tools. Go and try and Figma, go and look for Microsoft Visio, do your diagrams, use the right symbols and submit this work to me. And then somebody has sat down to, someone has taken pen and paper, drawn these things for me, and then take a snapshot of them and send them to me. Now, would you go and stand somewhere and say that you were taught, you came to study IT, computer science, but at the end of the day, they made you write things on paper? Are you still backward? It didn't make sense to me, and I think I am not going to give that person a fair score, in my opinion, because that's not what I requested from you. If you are at this level still fumbling to get access to a computer or know how to use it properly to get certain deliverables done, then you have a lot of catching on to do. You probably should have waited a year or two before you enrolled in this program. Nevertheless, I've seen people who never even could type a word, but as we speak, they have improved. Even prior to recording this video, I have met one of your colleagues who still doesn't own a computer, and the library and other computers sitting there have become her friend. She's improved and learned a lot from this course, and of course our engagement, to learn how to use a lot more of cloud resources so that she can also catch up and not to complain, and still making very good and decent grades. Yet there are some of you who are still folding your arms. Your problems are only known to yourself because you don't want to get out of those problems. You don't even want to share them, so that Mark will even recommend approach because you think I'm too direct and too harsh. There's no other way to sugarcoat the story. We have to tell it as is. Your future is important to me, even though you will not share your backs with me eventually. Right, so let's hit the nail on the head, shall we? So I'm talking about dependability, and I was using Sakai as a reference point. How some of you perceive it, and how some of you perceiving it rightly, and some of you perceiving it as a problem in itself. You are the user, I'm a user, and so when there's a degree of trust in the system, then we say that the system is highly dependable. This keyword has 3 subwords that are put together, or should I say these words are interdependent, but when we say dependability, it's a check. It's as if we are talking about computer security, where we want to ensure confidentiality, integrity, and then availability. We have 3 keywords, and these are reliability, availability, and security. Okay, So these are the three words. The user's degree of trust, it reflects the dependability of a particular system. And so if there's a widespread effect and large number of people are affected, then we have a failure. But if it is just a handful of people, then we assume that the system is working as far as normal use is concerned. Okay, so systems that are not dependable and are unreliable, unsafe, and insecure, the negatives of all the three things, the three attributes that I made mention of earlier, may be rejected by their users as long as there's a breach of trust. So the cost of system failure may be very high if failure leads to economic losses or physical damages. And undependable systems may cause information loss with high consequent recovery costs. So what could cause a failure? We could have a hardware failure, have a software failure, we can even have operational failure, which is more common in this part of our world. Okay, so there are principal properties of dependability. We have, like I mentioned, the availability, we have reliability, we have safety, we have security, and then we have reliance. These are very, very important properties. Principal, you can see the interpretation of all of them. The ability of the system to deliver, the ability of the system to deliver services when requested and when specified. These are availability and reliability respectively. We have more of this. Excuse me. We have safety, a judgment of how likely it is that the system will cause damage to people in its environment. We have security, we have resilience. These are very important principal responsibilities. Other properties of software developability will be reliability, maintainability, survivability, and then error tolerance. Yeah, we have the principal ones, and then we have the auxiliary properties, but all of them are important. So many dependability attributes actually depend on one another. Safe system operation depends on the system being available and then operating reliably. So that's how they work hand in hand. So a system may be unreliable because its data has been corrupted by an external attack, and we can talk about denial of service attacks on a system that are intended to make the system unavailable. That's the main purpose of a denial of service. We could even have DDoS, and that is more severe beyond the normal DOS. So if a system is actually infected with a virus, you cannot be confident equally in its reliability or its safety. So how do we achieve dependability? As a software engineer, you should have this at the back of your mind. How do we achieve this? One, avoid the introduction of accidental errors when developing the system. Design the VMV processes, we've spoken about this before, that are effective in discovering residual errors in the system. Design systems to be fault tolerant. Fault tolerant is very important. Design the protection mechanism that guard against external attacks. Configure the system correctly for its operating environment. I hope that you are not just creating databases on PHP, MySQL, on this MariaDB and exposing your client's databases. You make sure you have put the root password is set and everything is in place. I mean, all the constraints are in place to make sure it is safe for them. Don't go and disappoint me or disgrace me. You configure these things correctly. You include system capabilities to recognize and resist cyber attacks, and then you include recovery mechanisms to help restore normal system service in an event where we encounter a severe failure of some sort. So take notice of that. Dependability costs tend to increase exponentially, as increasing levels of dependability are required for two main reasons. The use of more expensive development techniques and then the hardware that are required to achieve higher levels of dependability, and then the increased testing and system validation that is required to convince system clients and regulators that the required level, that the required levels of dependability have been achieved. So these are the two main dependability, two main reasons as far as dependability costs tend to increase exponentially. It can be attributed to these two main reasons. We can also talk about social technical systems, and these social technical systems, we are literally just talking about software engineering not being an isolated activity, but being a part of a broader systems engineering process. So most of what we have discussed in this course, you will find them in system analysis. There's a whole subject called system analysis. Much of what we've discussed, translates to that place, because systems engineering is a whole big process and software engineering is just one brother of it. So software systems are literally therefore not isolated systems, but they are essential components of broader systems that have a human, social, or organizational purpose. So we can talk about equipment, hardware devices, and all these. One component, we have the operating system that provide the common facilities for higher levels in the system. We have the communications and data management. They have that's the middleware that provides access to systems and databases, remote systems and databases, the application system, the business process, the organizations, and then we have society where we have laws, regulations, and culture that actually affect the operation of the particular system that has been deployed. So we need to take note of it, and there are actually interactions and dependencies between the layers in the system, and the changes at one level rippling it through other levels for dependability. The system's perspective has to be considered as a key portion of it. We cannot ignore that bit. Great. Then we have what we refer to as the emergent properties of a system as a whole, rather than properties that can be derived from the properties of components of a system. So they are consequences of relationships between the system components, and they can therefore only be assessed and measured once the components have been integrated into the system. So these are emergent properties that we want to talk about, anything that falls into this category. And there are two types of emergent properties that we can make mention of. We have the functional properties and we have the non-functional emergent properties. The functional ones appear when all the parts of a system work together to achieve the same objective. We'll give you a typical example, like a bicycle having a functional property of being a transportation device once it has been assembled from its components. I hope you get a picture, right? And then we can talk of the non-functional emergent properties. Examples like reliability, performance, safety, and security, and so on and so forth. They are actually often critical for computer-based systems, as failure to achieve some of these minimal defined level in these properties may make the system actually unusable. So those are those. We have some examples of the emergent properties and their detailed descriptions outlined for you, so you may want to take notice of that. We proceed to talk about regulation and compliance. The systems don't exist in isolation. They don't exist in empty space. Organizations do not simply exist. There are registration processes, there are rules and laws, norms, compliance, etc. that they must all abide. Banks, without meeting certain compliances, don't get to offer certain services or even get licenses to operate. Just to give you a picture of what we're talking about. So many critical systems are actually regulated systems, which means that their use must be approved by an external regulator before the systems can go into service. Recently, the UK Parliament, the EU is requesting that everybody makes USB-C the standard for all devices, and so maybe Apple may eventually in the end may have to migrate from the Lightning to USB-C or something. But that's just to give you a picture of what we're talking about. So we can have nuclear systems as examples, air traffic control systems, medical devices, etc. So a safety and dependability case has to be approved by a regulator so that the system can work. And that's what we're trying to talk about. So we have regulation and compliance. Compliance, literally following the rules that applies to the social technical system as a whole, and not simply the system that has the software element of the system. So that's just it. There's a regulator. So if you want to achieve certification, companies that are developing safety critical systems have to produce an extensive safety case that shows that the rules and regulations have been followed through thoroughly to the very end. It's like engaging with a fund management company. They can have all the brand names and so on and so forth, but at the end of the day, the regulator has some rules that they must follow. If you're developing software for such a client, you have to make sure you meet every single requirement in that regard so that they remain compliant. If they don't have money, you also don't get money. So yeah, that is about reliance, regulation and compliance. We cannot have this conversation and ignore redundancy and diversity. Redundancy, keeping more than a single version of a critical component, diversity, providing the same functionality in different ways in different components so that they will not fail in the same way. We have process activities like validation, should not depend on single approach, like testing and validating the system. Redundant and diverse process activities are important, especially for verification and validation. So we can have multiple different process activities that will complement each other and allow for cross-checking to help to avoid process errors, which may lead to errors in the software. Yes, so to ensure a minimal number of software faults, it is important to have a well-defined, repeatable software process. Repeatable processes. That's why that has been highlighted. So a well-defined, repeatable process is one that does not depend entirely on individual skills. Rather, it can be enacted by different people. So regulators actually use the information about the process to check if good software engineering information, good software engineering practice has been used. And good software engineering practice is when there's been a whole team involved, individual with their specialties as defined in the developers on the project, with their skill set have all done what they has to do, due diligence, etc. Not a solo one. So you take notice of that. So for detection, it is clear that the process activity should include significant effort devoted to verification and validation. So what are some of the characteristics of dependable processes? We have the explicitly defined and the repeatable. These are the two key words. When we say explicitly defined, we are talking about the process that has a defined process model, a process that has a defined process model that is used to drive the software production process. When we say repeatable, we are looking at the process that does not rely on individual interpretation and judgment. So the process can be repeated across projects with different team members, irrespective of who is involved in the development. So what are some of the development process activities? Let's look at some of them. We have the system modeling, we have design and program inspections, we have the static analysis, and we have test planning and management. These are the main activities of dependable process. Now, developable software often requires certification. No two ways about that. They often require certification. So both process and product documentation has to be produced. It definitely has to be produced, no matter what. Upfront requirement analysis is also essential, actually, to discover requirements and then requirement conflicts that may compromise the safety and security of the system. So these conflict with the general approach in agile development of a co-development of requirements and system and minimizing documentation. These conflict with the general approach in agile development of co-development of the requirements and the system, and then minimizing documentation. Okay, So, in conclusion, we say that an agile process actually may be defined, and it would incorporate techniques such as iterative development, test first development, and user involvement in the development team. However, so long as the team follows that process and documents in their actions, and I repeat, so long as the team follows the process and then the documents their actions, and agile methods can be used. However, additional documentation and planning is essential to a pure agile and is impractical for dependable systems engineering. So on this note, thank you very much for journeying with me, and I'll see you again in the last session.